Hey everybody, and thank you for joining to another live stream of hacking on the Raspberry Pi Pico and the Pi Pico emulator. And today we have a very ambitious goal. We will try to get to complete PIO, or at least most of it. For those who don't know, PIO stands for Programmable I, and it's one of the unique peripherals of the Raspberry Pi Pico. And I mean, we started last week. It was pretty intense. We got, I think, about halfway through, a lot of to-dos. So this week we want to try to finish it as much as we can. Let me share my screen and let me know in the chat if you can hear and see me. And before we dive into the code, let me just quickly review what happened since last week. Not too much, but still. So this is like our commit from last week. We implemented the beginning of the PIO, and we have a list of things that we need to do. The last thing on the list was tests, lots of tests. So we held another spontaneous live stream on Thursday, where we created a bunch of tests for the PIO instruction set, and we verify those tests against the silicon just to see that the tests are correct, but they still don't pass because we are missing a lot of like the actual PIO functionality in the emulator. Yeah, this is just like a small refactoring. We also had a few bug fixes from Valerio, who fixed 2 bugs with the shift instructions, where you are shifting by more than 31. So if you are interested in the details, check them out. Valerio did this with GDBdiff, and Hackaday also wrote an article about GDBdiff last week, which was pretty cool to see. And then I released another version with those fixes, and I think at this point the instruction set is pretty stable and reliable. Okay, so after we did this spontaneous session with the PIO instruction set, we had one test that didn't really pass. Valerio sent a pull request to fix it, just like masking out some irrelevant bits. So we look at what we should be looking. And today I also fixed some of the PIO assembler tests. They broke when we refactored the API to use booleans instead of numbers. And we didn't fix the test, so they broke in this last session, but I only found out about it today. And thanks, Steve, for the feedback in the chat. I really appreciate that. Cool. So one more thing before we dive into the code, I introduced it on the spontaneous stream, but for those who missed it, this is a new tool I'm working on. It's just the PIO ISM. So PIO ISM is a tool from Raspberry Pi that translates program from code from, let's delete this, translates codes from the PIO language into either C, Python, Ada. I don't know who is using Ada to program the Pi Pico, but apparently this is a thing, or just, you know, hexadecimal, like the hexadecimal values of those instructions. So I made a web version of it. So usually you would just copy this into a file, then compile PIO ASM from the Pi Pico SDK on your computer, and just use the command line to translate this into this. But now you can just, you know, edit thing and see the result immediately. And this is the way I like it. This is the way I like to work, to get immediate feedback. And you have like basic syntax highlighting, autocomplete. Let's say I want to IRQ file. Oh, yeah, IRQ or wait or whatever. Actually, it didn't autocomplete wait. Well, we found a bug. I will fix it later. Anyway, yeah, you can use all those like directives. Yeah, no autocomplete for them as well. Okay. Oh yeah, I think this is just an older version. If I reload, then we'll get the, yeah, now we get the autocomplete. So yeah, that was the bug, just an older version. So yeah. Anyways, yeah, and now it doesn't compile because we didn't tell it what to wait on. Yeah, anyways, we'll figure this out later. I guess the issue is, I don't know. Anyway, we are not here to debug PIO ASM, but probably something is not correct with the syntax. All right, so let's get back to the code. So yeah, where were we? So I will just close this terminal so we don't have it's not disturbing us. Yeah, there is like all those tests that we created in the last spontaneous stream, and they are, most of them, if not all, are failing. Yeah, some are still passing because we haven't finished implementing the PIO, and they tested PIO. So let's go into the PIO and start. I think there are two ways to go about it. We could either go over the to-dos, and I think we have a bunch of them. We have like 15 to-dos, so that's one way. And another way would be just to go over the tests and like try to fix them one by one. So I think we'll start with those throws, because I think they are, go away. They are both used by some of the tests and by like they are to-dos. So let's start with them. So we have like those methods that set the out pins and the out pin dirs, and I think each machine should have like its own copy of the out pins, and then whenever you update them, they sort of tell the PIO peripheral. Let's actually move this so we have this full window. So there is like this PIO somewhere here. Yeah, the PIO peripheral. No, I don't want this. The PIO peripheral, and then it has like 4 state machines, and the state machine is actually the B class that implements everything. And yeah, and let's see. Yeah, we have like so eventually the PIO has to collect the status of the pins from all the state machines, and then report them to the Gpio, or I think the pets, one of them, doesn't really matter. I think in our case it will have to go to this Gpio Pin Class eventually, and if this Gpio pin has this function of PIO, right now we only have SAO, but if it has PIO 0 or PIO 1, and we'll probably get to it soon, then it should just read the value from this peripheral. So this peripheral will have will just collect the values from the pins, and it will also need to tell the this Gpio pin whether any of the values change, because we have this listener that we should call whenever the pin value changes. So we should notify this Gpio pin whenever there is a change. Anyways, so the first thing we want to do is just like to have internal values for the pins in the peripheral, I think. So let's have another register out pin values, and that's it starts with a 0, I think, and out pin direction. So either they are in or out, because we can control both the value and the direction of each pin with this out command. And then when we have set their pin, this dot out pin values equal value, or no, out pin direction equals value. Hey Valerio, good to see you here, and as usual, thank you for all the things you have done this week. It's really helpful. So out pin values, and finally it's sort of implemented, but we also need to update the peripheral that we did some change, like the pin values have changed, so it will be able to update this .pio.pins changed. So it will be able to update the so for now this .pio .pin changed won't do anything, but eventually to do notify the relevant GPIO that something may have changed, right? And then I think there is like and that's the next step here is there are like those debug registers that the test use extensively, and those debug registers I think we have them here paired out, just contain the values of the current values of the pins. So we can probably calculate them by let's add another getter, get pin values and get pin directions. And for pin values we are just going yeah, I think so I think we'll have a register that holds this actually. So we'll have pin values equals 0 and pin directions equals 0, and those will probably be private. Okay, private, and this is also private. And then we can say this dot, maybe we should instead of pins changed, we should just say how they changed. So yeah, I think there is like I don't know if we have getters for this, but there is like, so out pin values, yeah, so I think there is like maybe pin values changed and then a value, but we don't change all the pins. They are like there is like this mask, and I don't know if we have getters for this, but there is like this base pin and pin count that has to be changed, and I think we don't have getters for them. So let's create. So if we take a look at the datasheet, that's here, registers. For each state machine there is this pin control. So it has like this out count, how many pins are asserted by out pins or out pin dirs or move pins. And then we have also the out base. So let's actually create getters for all those because we are going to use them. So yeah, so we'll just copy this and we'll somehow figure out a way to manage this into code. That's ugly. Yeah, so let's just remove anything that is documentation, and then we'll be able to just edit this in a nice way. So so what we are interested in is basically the second number, which is the starting bit. So get, and then we can return this dot pin control shifted by this number, and then we also need to mask, but bear with me, we'll just do it by looking from at the datasheet how many bits we need to mask. And I wonder if there is like a way to camel case it. I'm not sure there is like a shortcut for this. That would probably be a bit helpful. Yeah, there is no easy way to jump to the right place, so I'll just do it half manually. So count, and then for those 4, that would be base. Okay, and the last thing we need to do is just mask them, and the mask would be so this is like 5 bits. This is, I think, all the bases, I think they have like the same number of bits, right? So 5 bits, yeah, that's probably also 5 and also 5. So we can mask them all with 1F, and then that's the basis. And for the count, I think this one is, yeah, I mean, we can see it by the difference. So this one is actually 6 bits, the out count. Like the differences here are 5, but then here, let's see, out count. Yeah, it's 6 bits because it can be 32. I see. So that would be 3F, and then this is like probably just 4 bits, right? 26, 7, 8, actually 3 bits. And then this one is probably also 3 bits. Yeah. Okay, so we have those getters, and then we can probably take the value, and we need to mask it. So const mask is this dot. We just want to take, or maybe we can just shift it by the pin base. And I think this is like, I'm not sure, but I think that the pins wrap around, if I'm not wrong. Yeah, so out base, we'll build the data. Yeah, that's a good question. I think they are wrapping around. Let's see, pin mapping 32, but we don't have up to. Okay. Each of the operation, 1 of 4 continuous, base. Okay, we are doing that. There is a range for each and side set. Cover any of the Gpio, that's 30, and the ranges can overlap for each individual, 8 writes. Okay, from the highest. Okay, so that's good. We have to run the machines one by one. If the same state machine perform and the side set is used, if no state machines write. Yeah, I don't think they are. I don't see anything that says this is wrapping around. So maybe it does, maybe it doesn't. Well, we can maybe to do check if this wraps. Otherwise, we can just shift this by shift it to the left by 1, or maybe we should just pass in the shift this dot shift. That's in, that's out base, and this dot out count, and then this this will just, you know, do the shifting and all of that. Yeah, maybe we will not even need this output pin values. I'm not sure. We'll see. Go away. We'll see in a moment. And then we have these pin values changed. So that would be pin directions changed, and by the same logic. And let's implement those. So we have pin values changed and new value number, and then we have first pin number and count number. And then we can say this dot pin values equals, we want to, let's have a mask. Const mask is just, we want, I think, count -1. So that should be, I think, the mask. So let's say count is 3. So count -1. No. That would be 1 shifted by count -1. So if count is 3, then 1 shifted by count would be this, and then yeah, we'll have this mask when we -1 it. So that sounds good. And we want to shift it by the first pin. and then we can say this pin values. We want to clear those pins, and maybe we can do this.pin values and clear the mask, or and then we want to take those new values, shift them and shift them by count by first pin, and finally mask them. So we only can take the relevant pins, and I think that's good. If not, one of the tests will shortly tell us. And same for pin directions changed, but instead of pin values, it should be pin directions and pin directions. Okay, and now we can start working on those debug registers. So when reading from those, there are like a few debug registers. These are like for the FIFOs, and after the FIFOs, we have small bunch of debug registers, or after the FIFOs, yeah, dbg pad out, all of those three. Let's implement them. Oh, we already have them. So radio int 32, that's the state machine, and yeah, so that's the general read. So case this return this dot pin values, I guess, and then for there is like pad out and pad out enable, that's the direction, pin directions, and finally, just for the sake of completeness, we have this CFG info. We just have like an hard-coded value, and I guess the easiest way is just to read it from the actual Pi. So let's quickly do this. We have GDP, and then what's the base address for that's print, and then the base address for PIO plus 44, so that's plus 44, and let's print it as hexa. So yeah, so this is like it says here, it's just like I think 3 parameters, but they are also exposed here, like it doesn't change, like there is only 32 instructions and 2 state machines. Oh yeah, this actually changes. Okay, so it's not that easy. It depends whether we join the FIFO or not. Oh no, it doesn't change because there is one FIFO with double this depth, so it's just the default depth. So yeah, so it's hard coded. So what was that? Just return this spatial value. So yeah, 32 instructions with 4 state machines and 4 FIFO entries. That sounds about right. And let's see what happens here. We have an error from the test because this.pio.pins value change is not a function. Didn't we fix that? We do have such a function, so why does it fail? Are there any other errors in? Oh, there is pin directions and pin, not pins, pin. Okay, all right. And yeah, I guess at this point, some of the tests may work, may not. Do we have any more greens? No, not really. I hope that after we implemented that, but there is like also this, in addition to the, yeah, we have here, what's going on here? We have the set pins, and we are using the set instruction here. So I guess once we implement set, a bunch of those were like, once we implement those set pins, a bunch of those tests will be green. So let's see what happens. There is set pins, which is not implemented. So in a similar fashion, we can also have like, not sure if we should actually set pins. If we should actually store the value, or just, you know, value number and set base and set count, and this is actually for pin value changed, and this should be value. Okay, this is green. That's a good sign already. And let's see if there are any more. Yeah, I think this one wasn't green before, so that's a good sign. First green test. And there is also move pins. And what does move pins do? Maybe we should implement that as well. I think it should call. Let's focus on this test, so we see what's running here. So where is this move instruction? Yeah, there is a set move destination, and for pins, don't we have move pins? Yeah, we are calling set out pins with a value. So we have either there is like this one doesn't work correctly, or this one doesn't work correctly, and there is an easy way to check. We can just print this value here. So yeah, we can see set pins, and oh, wait a second. Where is this set X? Set X. We can probably just before the move. Where is this move? Execute instruction. Yep. So move, where are you? Move, where are you? Yeah, let's print console log this.x to see if x was set correctly. And yeah, it's 8. So this instruction probably executed correctly. So we have a problem with the move. Let's see what's the value. It should be console log. Actually, there is a better way to do it. Print wallaby debug value. Yeah, Control Shift RV. I'll try to remember that. And then we can see here it's 8, and then we can see here it's also 8. So yeah, it should probably write 8 to yeah, but it doesn't write 8. Let's see why. Oh, or maybe it does write 8 by calling set out pins, and let's see, value should be 8. Control Shift RV. I will, yeah, 8, good. And then we are calling this method, and now this first pin should probably 0. Yeah. And then the mask, the count should be, I don't know, I think it's 32. That might be the problem. I think the count here is 22, and that's, yeah, and that's probably where the bug is. Yeah, it's 32. So if I guess if count is greater than 31, then the mask is just all the pins. Otherwise, we actually do this masking, and it should be a question mark. Okay, and now this is green. Great. So one more passing test. Nice. And let's see what happens here. We get an invalid value, and what's the reason for that? Expected, received. So yeah, I think that the problem here, I remember this from writing the test. Yeah, Valerio mentioned that set pins and move pins use different bits on pin control, and I think we implemented that, like set pin. Yeah, there is like this set pins that looks at the set base and set counts, and then there is like also set out pins. And this one looks at the out pace and out count. So yeah, so it's using the same method to update the peripheral, but it's using different bits from the pin control. So I think that should fix that. Yeah, and I think the reason we are getting this problem here is that it's returning it's setting the highest 2 bits by looking at the received value. It seems like a very big. And what we have seen from the debugging the silicon, that those bits are always low. So when we are reading, we can do it in the right way to do it would probably just to, you know, mask the whole thing. So it's always like, yeah, always the 2 lower bits are, yeah, missing 1 F. The 2 lowest bits are always low. So let's do that here and also here. Yeah, maybe another set of parentheses just to make sure we, yeah, okay. Yeah, I think we also need to do the same here in this function. I have a feeling it works. Should be the same. Yeah, and now let's see what happens. Okay, this is green, that's great. This is also green, that's great. So we can see that now most of the tests are green, and that makes sense because we implemented most of the instruction, but we were missing the connections with the pins. Here we have something interesting. So yeah, all those conditional jump instructions, they fail. So that's interesting. Let's see what happens here. So we set X to 5, we set, we jump to 8. Oh, wait a second. Why did the address increment? It shouldn't increment when we are executing instructions like this. I think this is the bug. So there is like PIO, and then there is execute instruction, and it probably has like, yeah, it has this update PC equals true, and then it updates PC. But we shouldn't update PC if we are executing it because of out exec instruction or because of writing to this instruction register. So let's have update PC equals true. That's the default. And then when we call this, where do we call it? So when we call it, we want the reference, not the implementation. Yeah. So yeah, so here, when we call it here, we don't want to update the PC. And yeah, and now it became greener, which is great. Like this test passed, and let's see, all the other tests pass. And now we have this like thing with the OSRE. That's pretty nice progress already. I mean, that's totally not an exhaustive test suite, but at least this is a good start. So yeah, JMP OSRE, so JMP not empty to 11, and it didn't take the jump for some reason. So let's focus on this and let's take a look at the code. So that's JMP condition, and then there is like OSRE out shift register not empty. Let's start by logging this value. What's this value? It's 0. The shift count is 0. So we should update it. So let's see. We are reading this address, and then we are moving into OSR from null. So probably moving into the OSR should do something, and it doesn't do it, or it doesn't do it correctly. So let's see, move destination and moving to the OSR. I think it should, yeah, it should reset it to 32. No, or maybe empty. It should be 32. Like it's full. So let's see. I think there is. This is from the datasheet, so maybe the meaning is, yeah. So I guess, let's see, OSRE. Yeah, compares the bit shifted with the shift count result by this. Yeah, so we should probably, we probably didn't implement this correctly. So if this dot out shift count is less than this dot, not touch list, this dot pull trace. And let's, oh, we do have it. Okay, and now this should be green. Yes, now I think it's or less than or equal, I think. No, less than. So if it's less than the threshold, and that would be 32 in case the default result is 32. And if that was less than or equal, then the test probably wouldn't pass. Perfect. Okay, next. Now we have like an issue with the pull instruction. What happens here? So expected 0, received 1. How comes? We just pulled from this tx0. So let's see what happens when we pull. Let's focus on this test. Where is pull? So pulling, that's out, and pulling. So pull, and then we didn't implement this pull because if full of empty, or yeah, probably this is true, pull if full or empty, but I think we might have decoded it incorrectly. So yeah, maybe we shouldn't have knotted it. I think it should be, we wanted to convert it to Boolean instead of knotting it, and yeah, now the test is green. That seems like it's more correct. Yeah, and then we have like this out exec, which I think we still haven't implemented, but wait a second. No, we still have a bunch of failing tests after that, but out PC works, which is cool. So set out, yeah, destination, or there is like a method for that. Out destination, write out value, yes, write out value, and then exec. We have this dot exec equals value and exec valid. So yeah, so I think we didn't like really take that into account, or did we? Yeah, I'm not sure. Let's see. I think here we disable the state machines, if I'm not wrong. So this is probably resetting them. And then we have like, but I think they are all disabled and they jump to 0. We clear the FIFOs and let's add a space here. We just reset those registers to the reset value. So yeah, but then I think in case of exec, we should probably just execute the instruction immediately. Yeah, don't think, yeah, we don't do anything with this, so we can probably do something like this. If this dot exec valid, then this dot exec valid equals false. This dot execute instruction, and we execute this dot exec, just the opcode. Maybe we'll call it exec opcode, and don't update PC. And let's change this dot else, and then to do delay, because we skip it if exec is valid. Let's change this dot exec, yeah, to exec opcode, because it's just the opcode we want to exec. And this is green. Perfect. Yes. All right, so there is a problem with the push, and I have a feeling it may have to do with the same thing as pull. Yeah. We fixed that for both of them, I guess. Let's see what's going on here. So the problem is what we had in X. So what we add in X. So the FIFO should have the value 9, but we got 0. And what's the reason for that? Let's see. We move 9 into X, then we are in. So this should, let's see what's going on here. Let's focus on this test. And PIO, and then that's inside in instruction. So I think we still haven't really looked into in. Yeah. Execute instruction. Where is in? There we go. And then let's see. Bit count is 0. Then we are just we are in 32, which means we go here. So we just copy the source value. Let's see what's the source value is. So it's 0. It shouldn't be 0. So maybe the problem is somewhere here. Yeah. So in source value, what happens here? We are reading from X. So is this dot X, is it 0? We are reading from the right register. It's 9. So how comes, yeah, something here is probably, why do we need this mask? What's this mask? Bit count, and the bit count is 0. Yeah, I can see the bug here. So let's put it here, so we have a bit more space to work. So yeah, so basically we are reading this value and we are masking it, but we shouldn't be masking it if yeah, if bit value is, so let's make this a variable, and then we only mask it if the bit count is not 0. So source value, so we don't need to mask it in case we just want the whole value. And now this is green as well. Nice. Right, what's going on here? So here we have the IRQ instruction, and I think we still haven't implemented that, so that's why it fails. So I think that's a good time to implement wait and IRQ, because the next few tests that fail actually they use those instructions. So we need them. Other than that, all the other I don't know how many, I think we had 19 tests. Let's see, 21 tests. So the other 21 tests they pass. So we only have like those 4, the other 17. And then we have those 4 that are waiting for IRQ and wait. Okay, so that's exec opcode, not exec, yeah. Okay, and then we have like this IRQ and wait. So let's start with IRQ, and we have like a bunch of registers. So how do we decode this IRQ? So have like clear, wait, and index. So start with index is just argument 1f, like the lower 5 bits, and then this is like out is just if arg and 20, so this bit, then, and we want to make it boolean, and that was like wait, and then there is like clear clear is just need double parentheses arg and 40. Yeah, that's this bit. And then so yeah, we have the index, and then if clear one, then clear the flag selected by index instead of raising it. If clear is set, wait has no effect. If one, halt. So there is a need to so if clear is set, then it's simple. Otherwise, we have to take care of wait. So let's start with this. If clear, then we need to do this. Otherwise, no, I want to do this somehow. Okay, twice, just once. Otherwise, if wait, then halt. Yeah, we will need to implement waiting in some way. Else this is just setting the bit, the interrupt. And then we have like Irq Index from, so that's the 3 LSBs. So I guess we can just take, instead of doing this, we can just take Irq. That's the Irq number. And then there is like this behavior. Irqs, okay. Thing, bit2. Okay, so now there is like, let's make it like that. Let Irq, and then if arg and if this bit is set, I don't know how to call it, but it's maybe there is like, I think there is like let's see, they call it here rel, so let's call it rel. Const rel is just args and this, so if rel, then it says that the Irq number is changed in a way, just modulo 4 addition on the 2 LSBs. So we take Irq equals Irq and just the high bit. That would be 4. And then we take plus Irq and, or it could be a bitwise, or they shouldn't overlap anyway. Irq and the lower bit plus this dot index. Do we have like the, there should be a way for us to know what's our index. Yeah. So yeah, and we could do modulo 4, or we could just bitwise end it with 3. That would be the same. And it's, yeah, we are still not using. Okay, so now we have like the Irq number. Hopefully we did this calculation correctly. And let's oh, and Peter, thanks for the comment in the chat. As you can see, it really makes me smile to read this kind of comments, so please do keep them coming. I love reading them. Okay, so where are we at right now? So yeah, we want to be able to set the Irq, and I don't remember, there is like a register for the Irq. I don't remember if it's, I think it's per state machine, but it's not one of those state machine registers. So each state machine has like those address, instruction, pin control, shift control, exit control, and clock divider. But I think there is like a bunch of other registers for yeah, I think row interrupts is the one that controls the Irq, and they are all shared, or maybe not. Yeah, there is like there is another pin that controls the Irqs. That's another register That's, I think it's called Irq. Just Irq. Yeah. So yeah, so there is this Irq register. So once we have this, we can, and this is shared. This is a right-click register. So let's implement this. So it's a peripheral register. So do we have here this fdebug? What does it do? Okay, not sure. Oh, it's for the FIFOs, but why is it 0? Yeah, I think it's just a few flags, but it should probably go with the other registers. And then we have Irq equals 0, and then yeah, we have like the ability to read this Irq, and it should probably come after all of those, right? 30, and this is 40. Yeah, so for all these debug registers. Case Irq, return this .irq, and then there is also Irq force. Right one to clear. Effects PIO int f is. So yeah, so that's if the software wants to set an Irq, and I don't think you can. Yeah, so this is just the way it's WF. It means probably it's not read only. So I guess you can write, let's say that reading from this Irq force always returns 0 because it's not really implemented, as far as I can tell. And here, case Irq. This.irq, and then this.irq updated, because if we have a state machine that is waiting on an Irq, we should probably let it know. Case Irq Irq force. So in this case, we are just, it's right clear, so we are just clearing those bits. And if we are Irq force, then we are setting the bits. Yeah. And again, this.irq updated, break, and let's implement Irq updated. For now, it doesn't do anything but to do notify state machine plus also we need to update the CPU Irq registers, which we'll probably do next. I don't think we even have tests for that, but for now let's go back to the Irq implementation, and then if clear this dot machine.pio.irq, just clear this bit, one shifted by Irq, and if set, then we are just setting this bit, and then the only thing that's arg, not args. Only thing we are missing is this wait condition, and let's see if this makes any of the tests pass. So yeah, we can already see like those two tests pass. But then we have like this test, which is actually waiting for an Irq, right? And we still haven't implemented wait, but at least the basic, this is, I think, actually Irq clear. There is, yeah, there is no like, oh, this is like, it's actually Irq3 rel, not 13, because it's Irq3. And it's a relative Irq, that's the bit, but we have just implemented, and we can probably see this getting into this if, yeah, it's green. Okay, and now let's do wait. So that's the last one, and then we'll have to also think about how do we wait, because we also have here like, yeah, this done to do. And I think in wait, in this case, so if it's not clear, then we are always asserting the IRC, but then if there is a wait, then we need to halt. So yeah, and also this.pio.irq updated. That could be a not so funny bug to hunt for, even though it happened here. I'm missing opening braces. Okay, so and this is not happy because we need to have curly braces around this switch case if we have any variables. Okay, so yeah, we still have to work out this waiting mechanism, and now we are going to implement the last instruction, wait. So we'll have to take care of that now. And let's see, wait. What does wait do? It has index, polarity, and source. So const pol is just arg, and that's boolean arg and 18 this bit. And then we have source arg shifted by 5 and 3, and we have index, which is just arg and 1f. And then depending on the source, we decide what to do. So but in any case, I think let's see. 0, wait for 0, wait for 1, source, what to wait on, GPIO or pin or IRQ, and then which bin or bit check. Yeah, so I think GPIO and pin have very similar behavior. That's waiting on the value of a pin to become equal to polarity. So if or switch source, so case 0, that's waiting on pin GPIO. This dot waiting through, let's have a variable that tells us we are right now waiting. This dot waiting type equals there are probably going to be 3 wait types, so let's declare a type for that an enumeration. So enum wait type, we can wait for a pin, for FIFO, and maybe we'll have 2 wait types for in RX, FIFO, and TX, I'm not sure yet, and also for IRQ. And then we can have like this waiting is wait type of wait type, and then we also have we can probably initialize this for false. Maybe we can just have none as a default value. Is wait type none. And finally, we also have wait index, which will tell us which pin or IRQ we are waiting for. And then here we can, in GPIO, the wait is for pin, and this dot wait index, I think it's just the index as is, right? GPIO absolute not affected, yeah. And then there is like wait pin, and it's very similar, but the wait index is calculated differently, a bit differently. So we are waiting again, and the pin, the input, then index select input IO mapping, and then index select which pin index to pin in base. Okay, modulo 32. So index plus this dot pin, yeah, that was in base, I think, yeah, modulo 32, right? Pin in base modulo 32, And finally, wait for IRQ. That's 10, right? That was 0, 1. And by default, we just do nothing. That's the reserved index. I don't know what happens. I guess it just skipped the instruction if it doesn't know it. So this dot waiting is true, and this dot wait type equals wait type dot IRQ, and then we have to calculate the IRQ index, and it says like there is also like this. Oh, we should also include the polarity for the wait. So yeah, we can probably just this dot wait polarity. Just have it here because its polarity was false. Because it's common for all the wait types, I think. Let's see. If polarity, then the state, okay, we'll have to take care of that. The flag index encoded in the same way. Okay, so we'll just copy paste it. So this dot wait index IRQ equals, so we are taking a index, but yeah. Maybe we'll just have a helper method here, and we'll reuse it. So it takes this dot takes index and this dot index, and this method will just we'll move it to the top in a moment. But basically, constrel is index and 10, and then return. If it's rel, then do this thing, and maybe we'll call this IRQ and machine index, and then if rel, then do this, otherwise just return IRQ and 7. And here IRQ. Okay, let's copy it to the top, and then we can let's move the enum before those functions, and then we can go back to waiting. Wait, let's see, wait, and then arg, yeah, and then here we just take the IRQ index with index and this dot index. That sounds fine. And then let's go also to the implementation of IRQ and change it. So just IRQ is IRQ index of arg and 1f with this dot index. Instead of writing this code here again, it can be a const. And let's see if the tests are, no, something is wrong here. Ooh, yeah, I think there is some problem. I mean, yeah, now, okay, back to normal, back to green. Wait isn't implemented yet because, yeah, we should, we implemented the instruction, and we can probably see that it gets into wait, and let's just focus on this one. So we can probably see wait is now green, and it gets, or maybe it doesn't. Interesting. Put them side by side. So wait. So we oh, wait a moment. This is a different kind of thing where we are actually enabling the machine. That's interesting. So in this case, we are writing 3 instructions to the memory, and we are enabling the machine. And that's the case in the next instruction, is in the next test as well. But we still haven't implemented that, as far as I can tell. I think we already have like this enabled. Yeah, so we are probably setting enable to true, but nobody is acting upon that. So for that, we are going to have to, we are going to have to implement some kind of, for each PIO, let's call it run. That will just for const machine of these dot machines and machine dot execute instruction. So basically just maybe we'll call this step. It will just actually I guess eventually that wouldn't be a good solution, because maybe each machine have a step, a method that will call execute instruction with the current instruction. This dot execute instruction, this dot PIO dot instructions at this dot PC, and I think we can move the update PC logic here. I think so. Let's try that. And then we don't have to worry about that in execute instruction. So basically step does want to update PC. That's just a single step. So it's true, and then unless execute instruction sets it to false, it will execute this instruction. And there is also this concept of clock cycles, which I'm not sure how we could implement. I think each machine should count clock cycles individually. So let's have another cycles, I guess. Cycles equals 0. And from what I remember, let's see if I can see it here, maybe here. Each instruction takes 1 cycle, plus there is like, fetch 1 instruction, takes precisely, unless it stalls. Instruction may also insert delay up to 31 cycles before the next instruction is executed. So for usually instructions, where is execute instructions, when they are executed, they will just after executing, they will this dot cycles plus, and if there is like delay bits, then we should increment cycles as well. This dot cycles plus equals, and then there is like this delay and side set, but these bits, like, they have 2 optional purposes, so it's depending on the machine configuration. So there is like inside where delay. Yeah, so there's like those bits that can be either side set or delay. So there is this field, and then there are like a few pins that are used for the side set, and then it's depending on the machine configuration. So there is like side set count, and then there is also a side en. So let's do this. So every instruction, and I think the MSBs are like used for the side set. So we need to know how many pins are used for the side set. Yes, the side set could happen right after the instruction, because I think it takes precedence over the instruction. So side set enabled if this dot set count yeah, maybe we should just say so yeah, so side set bits is this. Let side set bits, and then const there is like if this dot what was that, side n. Do we have like getter for that or something like that? That's side, I think, not shift, pin control, I think. It's a const pin control side n, and what's the value of side n? That's 30. Okay, so if this is, I think we can move this for full screen for now. So if this dot control and side n, then we can probably just plus if this, then 1, otherwise 0. That's pin control. Okay, and now we know how many delay bits we have. So const delay is just delay side set, and so we need to mask it with 1 shifted by 5 minus side. So we have 5 bits in total, and we only want the we want to remove all those side set bits. This can be const as well. So we want to remove all those side bits and just get like the remaining bits as the delay. So if side set bits is 5, then it would be 1 minus 1. It would be masked with 0. If side set bits is just 1, this is actually only if there is like any side set bits, then we need to add 1. So if there is any side set bits, then yeah, then we need to, so if there is like 1 side set bit, or 2 actually, because of the side n, so that would be 5 minus minus 2, that's 3. 1 shifted by 3 minus 1 would give us the lowest 3 bits as the delay. So now we can here, we can do if cycles plus equals delay, just account for this delay. And we should also do this side set. So if this dot side set count, and let's have another variable that will keep track of side en, because we need it here as well. So side en, just let's booleanize it. Yeah, so if if not side en, so if side en is not true, then we are setting the side set bits on every instruction. Otherwise, we need to check if the MSB, I think it's the delay. Like I think this, no, the MSB. If one, the MSB is used as a side set rather than a side set bit. The value of pin control side set count is inclusive of this enable bit. Okay, interesting. So we don't need to actually do this addition here because this number is inclusive. What was that? Here. We don't need to add, just, yeah. So we can probably just simplify the code here because this number is inclusive. Yeah, so and then so where were we? this doesn't get false anymore. So, oh yeah, that was like WAP if. So if this dot side set count and side E and not side EN, so we should always side set, or the MSB is set, then const side set. It's just this dot so delay, and then we need to shift it by 5 minus side set count. So if there is like yeah, we can probably copy this from this at the beginning instead of this dot. So side set count. I think we can move all those variables actually to the end, because that's where we use them. Make the code easier to reason about. So this equals this, and then we don't need all those repetitions of this. We can also copy pin control. We are at it. Pin control, and then let's see. So side set equals delay side set shifted by 5 minus side set count. So if side set count is 5, then we just shift it by 0 and we take all the bits. If it's, yeah, that sounds good. We should also like yeah, so then if side EN, this dot set side set pins, and I think there is like another, or let's call it just set side set, and it will take a look at the flag. There is another flag that tells us if it sets the pin values or the pin direction. So yeah, if it's yeah, so we are taking delay the side set, but then if there is like and then we are only taking side set count pins, or I think if side EN, then we need to take side set -1, because we don't want MSB, it's just the enable bit. Otherwise side set count, and then we can, it's not happy because side set count. Yeah, we need to decide if it's, yeah, I think we will stick with the datasheet, which says it's just written this way, side set, without like this is the word side set. Set side set, and then we have like set side set and value number, and then based on this flag, and this is side pin dir. So if this dot control, and there is like count, so if pin control and pin control, then this dot PIO dot, this is the pin dir, so pin direction change, and that's with value, and first pin is this dot side set base and count. Otherwise it's the same, but with pin values changed. And we only need to add this, and I think we have implemented the side set feature, or so I think. I don't think we have any tests for that though. It would be fun to start writing a lot of test cases for and finding all the mistakes that we probably have here. Yeah, so yeah, I think that was bit 29, right? Yeah. Okay, so one more feature implemented. We have those side sets and the delay, which makes me pretty happy. Yeah, that's long. I think we'll get to over 1000 lines. Okay, so this is machine.step actually. And yeah, I think we'll have to revisit it to to work with the clock, but right now I think there was like, yeah, this should, we'll remove this argument. Let's see if we didn't mess up with the other tests in the meanwhile. Yeah, they are all still green, which makes me happy. Only like those two, which requires execution of the state machines. Yeah, so the thing is, I'm not sure how. I think we are not even running the code in this. We are creating test driver and it calls. So yeah, I think we may have to start a CPU. What does CPU.init do? Reset init and set registers. So yeah, reset init holds the CPU, but I guess in case of the PIO, even though the CPU is halted, the PIO keeps running, so that's a special case. So in the actual GDB, the PIO always runs, and maybe that's something we should also do for our RP2040 test drivers. So when we are initializing, it's no longer left make this.rp2040.pio.start, and we'll implement it, or let's start both PIOs. There are two of them. Yeah, and eventually we'll probably need to somehow combine this into the CPU, but I'm not sure about that yet. So let's have a start method, and start will, that's a bit tricky, I think. Should probably be very similar to the RP2040, to the execute method of this, just executing instructions and then repeatedly doing so with a timer. So this dot step, and yeah, so we can have this get stopped, which returns this dot control, and there, return this dot machines, or for const machine of machines, machine dot enable. If it's not enable, then if there is at least one machine then running, then we are returning true. Otherwise, we are stopped. There aren't any enabled machine, then we are stopped. Enabled. Okay, and then start should probably yeah. So as long as we are not stopped, we should probably yeah, there are probably some ways to, maybe we'll call it run instead of start. It sounds better. And run timer, and then define this run timer, just like we have execute timer here. So again, I have no idea if that's the way I want it to be, but we need to start somewhere and then see where that leads us to. So now inside the test driver, we can just run those state machines, and I think they will be stopped immediately. So maybe, just maybe, I'm thinking they should probably be controlled directly. So let's refer that. Yeah, they should probably just, whenever we update the control, so if there is like ctrl, okay, so whenever we are writing to the control, so we can say if no this dot stopped. So if we are not stopped, then this, if there is at least one machine that is running, or we can just, you know, check if value and f. I think f is like yeah, that's the lowest bit. So basically, if there is any running machine, then we call this dot run, or yeah, we can probably say this dot if this dot stopped, and have a Boolean variable that will take care for that. Yeah, let's declare this Boolean variable instead of getter. So stopped. It's actually true. In the beginning we are stopped. So if we are stopped and const running should run. Let's wrap this in braces so it's happy. So if this is stopped and we should run, this dot stop equals false. Else if not this dot should run, if not should run, then this dot stopped equals. Actually, we can just do it like that. No, I want this to happen before run. So yeah. Yeah, I think that's good. Oh, bitwise end, right? Not bitwise, logical end. Cool. So now inside run, if this dot stopped, yeah, I think this is good. I think so. So at this point, we can see it's actually getting into run and running steps of the machine. Let's see what's up with the test. It's still not happy. So let's focus on this test. Yeah, maybe we should have a stop method. So when the tests stop, we clear all the timers. This dot stop equals true for const machine of this dot machines machine dot enabled equals false, and if this dot run timer, then this dot run timer, we are just clear timeout, and this dot run timer equals null. And then in the test driver, we can just stop all the this dot rb2040 dot PIO 0 stop and PIO 1 stop. And yeah, we expected 1, received 2. Okay, that's start. I mean, this means that something have started to execute, and I think the problem here is that yeah, we are stuck on the wait, but it continues to jump, and the reason for that is we haven't implemented wait. So I mean, we have implemented the wait instruction, but we still haven't implemented waiting. So I think the easiest way to do it is just inside step. If we are waiting, if this dot waiting, then return. We are doing nothing, and we can probably optimize it. So if all the machines are waiting, then we shouldn't step into them. And now it's still 2, because I guess whenever we are waiting, we should also not update the PC yet. So where is wait? So this dot update PC false in all those cases. Yeah, I think we should, we can probably, if source equals, if it's an unknown source, yeah, like 1.1, then break. We don't want to deal with you. Otherwise, we can probably always like set those two outside the switch, they are relevant for all those cases. And actually, maybe not so when I'm thinking of it, because yeah, I'm not sure yet. We'll see about it. But I'm wondering what happens if the condition is already true. Maybe we can check this at the end of the function execute instruction or something like that. Yeah, but for now, let's not worry about this too much. And it's true. So yeah, just have to worry about those. Okay, don't need this. Okay, so now let's just remove this and see if we haven't destroyed any of the other tests. No, they are all green still, despite all of our changes. Okay, in spite of all of our changes. And now when we are waiting, we have this waiting is true and updating this is false, and we can see we got past this. And then we set IRQ5, nothing happens, set IRQ7, and then we expect it to resume and clear the IRQ, but we still don't have this, this mechanism. So yeah, so whenever there is an IRQ, we should actually, first of all, before I forget, I won't forget because there is like IRQ wait. So let's implement it. So basically alt until the raised flag is lowered again. So this dot wait type is wait type dot IRQ. This dot wait polarity is false until it's false. And this dot update PC equals false because we are waiting. And this dot wait index is just the IRQ index. So now we also implemented this logic, IRQ wait, but we don't have tests for it, so it's uncovered yet. Eventually we would love to have a very good coverage of this file to make sure that there are no mistakes. Okay, so now we just need to implement this wait. So let's have another method that will, after execute instruction, just another method that will check for wait conditions if we are we have so many methods here, so many, yeah. Check wait. So if this dot or switch this dot wait type. So case if we are waiting for wait type dot IRQ, then if this dot PIO dot IRQ and one shifted by IRQ index. So let's const IRQ value equals to this, and this dot wait index, and then if IRQ value equals polarity, wait polarity, then we should no longer be wait. This dot waiting equals false. This dot PC++, because we need to skip to the next instruction. We sort of stuck on the current instruction, and I think there is like also this thing with the delay. So in case we are waiting, the delay should happen after the wait. So there is this thing where is this delay? Else if this dot wait, not this dot waiting, yeah, and if we are waiting, then we should probably store this delay. So maybe if this dot waiting else this dot wait delay equals delay, and we only want to, we'll create this variable in a moment, but we only want to update it if it's like a new wait. So if this dot wait delay, let's say that -1 means that we need to update, it's a new wait. So whenever we start a wait, we just set the wait delay to -1. So waiting, let's define this wait delay equals 0, and then, or -1. Whenever we set this dot waiting to true, we also this dot wait delay -1, this dot waiting there was another one inside the Irq. Where was that? Irq, this dot, oh, we should also say this dot waiting is true. Wait type, wait polarity, wait index, wait delay, update PC. A lot of yeah, maybe we should yeah, I think we should probably this dot wait to wait type dot Irq and polarity false and Irq, and this method will take care of all of those. So let's create this method. Wait type and then polarity and index, just making sure we don't forget to set any of those variables when we are waiting. And then this dot waiting equals true. Instead of doing this, we can just here we can this dot wait type dot pin and index and polarity. Yeah, let's just call this polarity and index. That's a simple one, and this one should get a different index. And finally, the last one that's Irq and with this index. Okay, that's a bit neater, I think, or so I think. And it's not happy because we still haven't closed this if in check wait. Remove it for a moment. So and then this dot cycles was, or we can do this. If not this dot waiting, then we don't have anything to check, and then here after this switch we can if not this dot waiting, so we stopped waiting, we can this dot update this dot cycle PC plus plus this dot cycles plus equals this dot wait delay. So we are updating and not sure, I think side set happens during the wait, before like waiting. There is anything about that? Is there? Side set. This makes side set more flexible. Side set is included. For things, number of MSB. Okay, we did this one and this one. And this one, and the pin there. Yeah, it doesn't say anything about that specific thing, whether we should side set, but I think it does it when it starts executing the instruction. So it makes sure it makes sense that we should apply this when we start waiting and not when we end waiting those side set pins. Okay, so there is one more thing about waiting for Irq. So I think it says that that was inside a wait. So if polarity is 1, then the selected Irq flag is cleared by the same state machine. So if we are waiting for it to become true, then and does that also happen in Irq? And wait until it's lowered again. If wait, so we are waiting for it to become low, not high, because we have set it to high. Let's just make sure that we did this correctly. Wait type.irq. That's inside wait. We are waiting for the polarity to be false. Okay, and then check wait. Yeah, so and then if this dot wait polarity or Irq value, they are actually equal. So if it's true, then we should also clear the flag, right? If that's inside wait. So if polarity is 1, so that's true. The selected Irq is cleared when the wait condition is met. So that's now this.pio.irq, and we clear this bit. Yeah. All right. And yeah, I think that's it for the Irq, and then case wait type dot. Yeah, there is also for a pin. So if this dot PIO dot RP, do we have access to the RP2040 yet? Dot Gpio at this dot that was wait index, so the pin index. So that input value, I think. Yeah. Just make sure that this has this override, so it seems good. So if this is Boolean, right? If this equals to this dot wait polarity, then we should stop waiting, and that's it, right? Yeah, we should probably just make sure this is not. Oh, and we need break after this one. And we should probably also check that this wait index, so we can probably do this. Yeah, I don't know what happens if you wait for a pin that is out of range, but let's just make sure this dot wait index is less than rp2040.gpio.length, just to make sure that we never run into trouble if somebody is waiting on pin 31. I think that should either always we should check it with the silicon, I guess, but that shouldn't happen. Nobody should wait on that number of pin, I guess. Now oh, hey Mark, you said you found one. What did you find? I would love to know. Good to see you here, first of all, Mark, you. And I would love to know what you found. Okay, so yeah, so I'm already seeing a message from someone in 5 years saying, yeah, you said this this should never happen, but I had this case where it happened. So if anybody wants to check what happens when you wait on a GPIO, let's say 31, if it always succeeds, always, if it's maybe it's invalid and it doesn't even wait, or I don't know, then feel free to do it and let me know, and then we can make sure this is always correct. And while at it, let's see what happens here. So To make this test, and we also need to do wait for FIFO. Let's fix that. It hurts in my eyes that FIFO is not written like this. We'll do it in a moment, I guess. How many to-dos do we still have, by the way? Yeah, we have 17. I thought we were. Yeah, I guess all these tools are like things we can now easily implement with this. Yeah, this is actually one to do. Delay counter, the waiting on IRQ state. Yeah, we can probably do that now in reset to do. Yeah, what is the delay counter? It only clears the waiting on IRQ state. What about waiting on GPIO? Any stalled instruction written or run by outmove exec? Any p left asserted? So I guess we can do this dot waiting just false, and then this sort of clear the delay counter, I guess, and the waiting on whatever state. Not sure if that's perfect, but that should be good enough. And I'm not sure how we can fix that as well. So let's remove it, and we only need to take care of out sticky, which we might not get to today, and wait for FIFO. Okay, so yeah, so we still need to now check if we are waiting. So we can probably, the easiest way to do it would just be to check it inside step. So the machine, so if this is dot waiting, then just this dot check wait, and yeah, we'll probably need to figure out a way to update the cycles as we are waiting. They should probably increment, but that depends on the system clock. So that's another thing we should figure out how to do the clock. So if we tie it to the system clock, then we can't accurately execute PIO machines without the system clock being accurate. And if we don't tie them to the system clock, we have to synchronize them. Like in those cases where you're waiting, you should just wait, check the system clock and update the cycles accordingly whenever you are back from the wait. But we'll worry about that later. So yeah, and then after check wait, if we are still waiting, then return. If we stopped waiting, then we can just execute the instruction, the next instruction. And inside execute instruction, we should probably, yeah, if this dot waiting, then we can probably this dot check wait, because the only reason we would probably get here is if one of the instructions we execute, let's say the wait instruction, but there is a chance we shouldn't be waiting. So in this case, we will just check the waiting and check the wait, and that should sort of release the wait immediately if the condition already happens or is already present when the wait instruction executes. Right, so yeah, it still fails. It doesn't go past. Let's we are already filtering on this test, and we can see it gets into check wait, but it's never waiting. Let's see what happens. So we are writing wait, or let's see if the wait executes. It should. So yes, so wait executes, and I don't think we need this anymore because we have this dot wait that updates all those registers, and then we can probably remove this because we just like the switch won't get into any of those cases. Oh, and that's a bug. It should be a B here, and now when we fix that, we can see this goes here, and probably at this point the machine is waiting. But so this point we should probably a unicorn in your schedule. Nice. Nice, Mark. Cool to read this. So yeah, Mark is one of the students in this new Raspberry Pi Pico deep dive course. Tomorrow is like the last episode, and he's going to learn about the PIO tomorrow from not the implementation point of view, but like how to use it. Yeah, the implementation is pretty scary already. Okay, so we are waiting. So wait happens, so we should probably get into check wait, and yes we do, but the only question is why is the IRQ not set? And we are also executing this IRQ to set. Let's just, console.log this.irq to string 2, just to get the bits out of it, and is super slow. It's still running the tests, running, yeah. Ooh, running this function a lot of, it's hard to get to this list, but maybe we can see it here. Always 0. But I'm pretty sure we are setting this IRQ with this IRQ instruction. Let's see what's up. Yeah, and also that reminds me, whenever there is like IRQ updated for these machines for class machine of these machines machine check wait. So whenever there is an IRQ update, maybe one of the machines, oh, that fixed that. Interesting. Yeah, now yeah, I'm not sure why it fixed that, like why I didn't get into check wait before, but that's good. Like that's probably should be checking the wait, and so we still need to update the CPU IRQ registers, but we already have notified the state machine, which is cool. And we got one more passing test, actually 2 more passing tests, which is cool. So first time we have all those tests running. That makes me happy. Almost 2 hours into the stream, but now we have probably somewhat good enough PIO implementation. We are still missing a lot of stuff. Let's just quickly review what we had in the last commit. We had like this checklist of things we wanted to do. So connecting the IO to the state machine, we only connected out set. We still need to do int, and maybe I will just copy it so we'll have it as a quick reference to make sure. So tests, we did some of them. Site said we did. Debug registers we did. This one still not. Clock cycles, sort of. Interrupts and IRQ wait we did. And connect we still need to do in and jump pin, but we already did out and set. So we probably did about half of what we have to do, but I think some of those things are not, like we already did delays. We didn't do the clock divider. Yeah, let's do this FIFO thing. Yeah, and by the way, I'm pretty happy that we were able to write those tests in the last spontaneous session just using the datasheet, and for the most part it just worked. It means that the datasheet is written in a way that is easy to understand, because we could write tests just from the information. And on the other hand, I'm pretty happy that we managed to use, again, the datasheet and implement it without looking at the tests for the most part. And the tests are passing, so that's another good sign. Anyway, so where were we? We wanted to implement those wait in the push and pull. Yeah, I think we'll just have 2 type of wait conditions. So we'll have RX FIFO and TX FIFO. That will make our life probably easier. And then there is like push, I think, and pull, and they have this wait bit. So So yeah, so we have to set this bit in case. So let's do this. So this dot wait. So if we are blocking, we are waiting for so that's wait type. We are waiting for the TX FIFO, and there is no polarity. We don't care about it, and no index. We're just waiting for it to be. And then I guess the same. Yeah, guess we could probably just yeah, I guess we don't need this break. We can just set the output shift count to 0, and that would be fine. Whenever we stopped waiting, I mean, we'll just fill the output shift reg and not have to worry about this. And the same goes here. Like if we are waiting for the RX FIFO because it's full, so we can't push anything into it. So yeah, now let's implement those check waits. So case wait type dot rx FIFO, and then if it's not full anymore, then this dot waiting equals false. And let's see, that was for pull, I think. So, or for push. So we should just shift this. Oh, actually here can probably this dot input shift reg, just use this as the index. That's the value that we want to push. So if it's not full, then this dot rx FIFO dot push this dot wait index. Yeah, and then case wait type dot tx FIFO. Then if this dot tx FIFO, if it's not empty, then we want this dot waiting equals false, and I think that goes into the input shift register. It's always confusing. This dot tx FIFO dot pull. Let's just make sure this is the correct one. Output shift reg. Of course, I had to mix them up. Output shift reg. And it's not happy because I'm missing a break here. Let's also add a break here. And we don't need to wait for FIFOs because we just did. Great. So I think we just implemented blocking reading and blocking waiting. Let's see. So I don't think we had. Oh, wait stall until some condition. FIFO is not full. I think we did that. Yeah, let's do this. Connect the IO pin. So there is like this in instruction that should be able to read from pins. Where is this in source value? Pins, this dot pins. What is this dot pins? To do. Nice. So basically we should just read from yeah, let's read the documentation, but if I'm not mistaken, we should just, and there is probably also used in move, right? Move source, or is it the same? Yeah, it's the same. Oh, so we also need to do this dot status, I guess. Yep. So let's do first of all get pins, or maybe we'll call it in pins, just to clarify that it's related to the in instruction. And where is that? The in pins. I'd say pin mapping. So there is like in. How does it work with in? think there is for in there is like it's just a shift, not count, but I'm not sure. And we can probably take a look at this registers, maybe. No. Maybe in the in instruction there will explain how this works in pins. So yeah, pins just says pins. Direction, I think we already do. In will also push. So yeah, we'll also have to take care of this. Insignificant. In 5, 5, 6, 7. Okay. That's not interesting. For us, maybe inside the move, because it also has like same mapping as out, and here same as in, but there isn't any information about that. And there is this, and I think, oh, I think we haven't seen this yet. Gpio mapping. So in set, and there anything about in? It's only for out and set. And this wrapping after Gpio 31. Okay, so writing probably wraps. Should probably do that. Wrapping. Okay, so let's add it to this to do wrapping after pin 21. Okay, so now we know we need to do this, and let's go back to in pins and let's give the information about how that works. PIO in data 32. It says it rotates them. And then it rotates them, I guess. So let's do rotation. So const pin values is this dot. I think we have this in the SAO where it prints all the pin values. Pin Gpio in. So yeah, we just have this for loop, like what we should be doing. Yeah, maybe we'll just add a helper method for this this RP2040s. It's getting big. Yeah, get Gpio values, and that will just do this. Return result, and then we can use this here. The SAO, yeah. Dot Gpio values, and let's see if it's still green. No, it's not happy at all. Oh yeah, this doesn't compile probably for that. Let's for a moment just return 0. So we'll run the test and we'll see if this is, yeah, this is untested. We haven't tested this. So, but I guess this is good. This is okay. We don't need this anymore. Yeah. Okay. So we don't have tests. Too bad. That's a pity. So we can have const Gpio values this.rb2040, and then we need just to rotate them. So const that was in base, I think. There isn't in count, right? Right. So get rid of this, and then we need return GPIO values shifted right by in base. And then I guess we should also like have GPIO, that would be the rotation, shifted left by 32 minus in base. So let's see if, yeah, maybe we should check if there is in base, then we should do the shift, otherwise we should just return GPIO values. And then let's see if GPIO value, if in base is like 5, then we are going to remove 5 bit, like to shift everything 5 bits to the right. Yeah, we should do this kind of shift so it doesn't copy the MSB, even though it should always be 0 because we don't have 32 GPIOs, but whatever. And then 32 minus 5, that would be 27. Yeah, I think that should probably do the trick, rotating. Okay, so now we have this in, and we only need to take a look at JMP pin. So maybe there is no, not here, the PIO JMP condition, and then there is like to do. So JMP pin, I think there is like somewhere which tells it which pin it should use. JMP pin, branch on input pin, exec control. Where is exec control? That's probably another, yeah. Exec control bits, so const and JMP pin. Yeah, it's a few bits, so let's just make a getter for this. Yeah, we have all those getters. Let's add get JMP pin, and this returns this dot exec control shifted by 24, and that's I think 5 bits, which makes sense because it's a pin number. Right, and then JMP condition jump, and then if it's a pin, then we just need to check so obviously this can't be if this dot gp, or yeah, const GPIO this dot RB2040 if this dot and const jump pin this if, or we can do return jump pin. If it's within the GPIO, then GPIO at jump pin dot value. Otherwise, so we are branching if it's 1, right? If it's branch on input pin, branches on the GPIO. If the GPIO is high, yeah. If it's true, then we return true. Otherwise, if JMP pin is too high, then if it's like more than the GPIOs, then we just return false. And we are done with this. Now the pins should be connected to the IO, to the state machines. Actually, we still need to connect them from the GPIO side end of things, so we'll do it in a moment. What else do we have? Gpio Pin Class. And we have to do interrupts and IRQ, clock cycles, and auto push and pull. Let's do the interrupts. So we have done some of that, but we have like a few more registers we need to take care of. So we have done IRQ and IRQ force. And we have all those like IRQ. Each state machine has 2 IRQs, so there is like row interrupts. So yeah, we should update the row interrupts according to I think SM0 to SM3 are just like the lower. I don't know if it says here. It says it here explicitly, but I think they are like just the lower 4 bits of the IRQ. And then we have to, yeah, this should probably create a getter for this. And this is read only, so int r, get int r, and then we have like const result, and so this 8 bits, we just this dot irq, and we take the lower 4 bits and shift them by 8. And then we need to check a bunch of conditions. So txn full trans. Okay, so yeah, we need to check for each of the state machines if, oh, that's actually for a single state machine, but that's not the case here. We want this getter for. Can probably add it here before I leave this read and write. So int r. So yeah. So this dot machines starts with 3 dot tx FIFO dot full. Then that would be 80, otherwise 0, and then 3. Then the sequence. Then we want to go think from 2 minus, yeah, cool. And then here 4 to 1, and same goes for the Rx FIFOs, right? So this is like Rx FIFO, and here we just need to do like that. And we got this, it could be just return instead of const result. Yeah. Oh, yeah, without this new line. Okay, cool. So we have this int r. Oh, and this should be empty, right? If it's empty. Okay, and then I think this should be basically y by default reset, because it's empty. dx, let's just make sure that this actually, if the is set, yeah, it doesn't say anything about whether this means that the Rx is empty, but I think it makes sure that to yeah, to let us know if it's empty, or maybe it's not empty and not full. Yeah, Lucas is asking how I'm going to emulate this pin. So we have this Gpio Pin Class, so it sort of provides the users an interface to this pin, so the user can like when they are creating an instance of the emulator, they can just use rp2040.gpio let's say 5, and just call to a listener, and then connect the output. So the listener will be called whenever this pin is updated, and then the user can connect the output to an LED or whatever they want. So basically that's the interface. It's up to the user of this emulator to decide how to work with the GPIOs, but that's the interface we're giving them. Let's see if there is anything about this txn full. Maybe there is something in the SDK. Let's see, I think I have the SDK. That sounds good. Yeah, okay. Just the definition. Seems like nobody is using it anyway. Oh, finally. So it's not full and not empty. Okay, so we should invert the condition. So this is yeah, let's do it like that. It's not full and not empty. Now it's probably correct. So yeah, let's do we have like this register? Yeah, enter. So let's return that's in reading, so it's read only, so we don't have to worry about writing. Case int r return kiss. Return this dot enter. Yeah. Okay, so now we can read it. We have this, and then there is like interrupt enable, which is just IRQ1, and there is, I think there is like IRQ0 and IRQ1, right? So force enable, and there is like probably status, which is just this combination of all those registers. So let's do them. They shouldn't take too long. So PIO. So yeah, let's have like those IRQ0 enable, and I think the result value is zeros, right? IRQ0 enable. Int enable, yeah, 0 and force as well. Int enable and int force, and same for IRQ1 int force, so enable and force, and reading from them just returns this value, case int r. So that was IRQ0 int e, return this dot IRQ0 int enable, and same for force. And we'll also have like the third one, which is int status. So for int s, that would be int status, and that would be just a getter that would be calculated from those three values. And then same goes for IRQ1, and we have those reading. We still need to do those. We'll do them in a moment, those getters, but let's first of all take care of the setters. So case IRQ0 int enable, then this dot IRQ0 int enable equals value, and we only take the lowest 12 bits, so that's that. And same goes for int force IRQ0 and 0, and then the same goes for int, no, that's int f, and that's IRQ1. And I think we also need to add breaks here after each of those. Yeah, enable, force, enable, 1, force, that seems correct. And we should also implement those getters. So get, so this dot, I always forget if but we can probably test it in the SAO or something like this, which one wins. So in status, so this one doesn't have we had another peripheral, maybe the UART. Oh, in the timer ints, yeah. So yeah, force wins over enable. So basically this is just this dot int r. Maybe we'll change it from int r to int row. That would make more sense. And this dot IRQ0 enable, and this, or this dot IRQ0 force. Okay, and let's change this one to int row. And same goes for IRQ1 in status. Okay, and finally, I think we can copy that as well from the timer. Whenever we change something, we should probably, yeah, I think int r is read only here, right? This is read write, this is read write, this is read only, and int r is also, I think, read only. Yeah. So whenever we have like, yeah, inside PIO. So whenever we change any of those, like int enable, let's just run a quick check for interrupts to make sure that we update the CPU if there are any changes. Also, like, yeah, IRQ updated will also call check interrupt. So I think that should be fine, because whenever we are, what does IRQ update do anyway? Yeah, so yeah, that's this dot check interrupts, and then this dot check interrupts. I think the logic should be quite simple. We have this in the timer as well. Check interrupts should probably just, yeah, set interrupt. So yeah, we should have like the base index for interrupt when we will configure it. So let's do it. For now, we'll call it just I, but so basically this is true if this dot IRQ, that's the interrupt status, that's the int 0, IRQ 0 int status, and we want to convert this to Boolean, and same goes for I plus 1, and without this, just a method implementation, and that's IRQ1, and then we just need to get the IRQ number. So that actually changes per, so each PIO peripheral, there are 2 PIO peripherals, and each one has 2 IRQs, and let's find their numbers. Interrupts. So yeah, PIO is 0, so that's 7 for let's call this first IRQ. So let's add it in the constructor. Read only first IRQ, it's a number, and then here in check interrupts we can say first IRQ. So this should probably do, like, this set interrupt already takes care of like doing the updating the microcontroller with the status of the interrupt, and that's 7 for the first PIO and 9 for the second PIO. So let's update the constructor. Yeah, so this is like IRQ base is 7, and first IRQ here is 9 for PIO1. And I think we can check out, yeah, we have interrupts and IRQ. And I think we can do this, connect the IO pins to the state machine. So let's do this. So let's go to the Gpio pin, and there are like, that's what Lucas was asking about. There are like those functions that each Gpio pin has. So let's take a look at those functions. Yeah, Gpio. System description, Gpio, where are you? Overview. Yeah, functions, there is, oh, function select, yeah. So if it's function 6, it's taking the value from PIO 0, so that's PIO 0, or for function 7, PIO 1, and now we can sort of implement this. So that's like reading the output enable and the output value from the peripheral. So case function PIO 0, then const index RB2040 equals this. I guess we can probably move this to the top because, and also function select. Yeah, so we don't need here this. And yeah, we can probably use this as well. That would make our life easier. So if it's PIO 0, then return this.rb20. We don't need this. rb2040.pio 0. Now we need to get a pin. Isn't there a getter for like yeah, let's, I think they are like, we have those, but they are private, so let's make them not private. Yeah, I think at some point in the future we'll probably want to go over the variables and make some of those private again. And just, I mean, we only need a getter here. We don't need other people to be able to change them anyway. So pin values and bit mask, and same for default result false, and same for PIO 1. So basically that's letting the output, and then we have also the same for the direction. Let's copy this small refactor. So yeah, and then here it just instead, okay, that was for the output enable, that was for the direction, so that was for the, that's the value. Okay, and here we actually need the pin directions. Okay, and we also need to be able to tell the GPIO whenever there is a change. For the input, we already wired it, I think, like we are reading from the GPIOs in the PIO peripheral, but we also need, there is like this check for updates we need to run whenever one of the pins might have changed. So I think we can copy this from the SAO, because maybe at some point we'll like, there is like this pin to update. So yeah, let's do it inside, that was inside PIO. So whenever something updates the pin, const pin values, so that's the old value, and then so pins to update is just whatever changed between pin values and the new value. Maybe const new value equals, just to make it a bit more clear. So if pins to update, and then this dot pin values equals new value, GPIO pins updated, and then it can take pins, or maybe we'll call it notify GPIO update, and it will take updated pins, and then we'll just move this loop there. So yeah, so new values, so that's XOR with pin values and new value, and then it's, why isn't it happy? Duplicate. How comes it's oh yeah, we have a new value, or so maybe we'll call it yeah, just will be value here. It's just value. Okay, so pins to update. Well, we can probably, if updated pins, then do this. Just call this dot notify Gpio updated with pins to update. Okay, same here. Pins to update, updated pins. Okay, cool. Yeah. So now it's also connected to the GPIO, and it should notify the GPIO pins whenever there is an update for the VIN values. And let's do it also for the pin directions. So let's do the same. Const pin directions equal this, and then const new value and this dot pin directions plus new value. Yeah. Yeah, we can probably just make our life simple. Remove this extra variable here. Okay, cool. So yeah, so at this point we are probably also playing nicely with the GPIO. So basically any change to the PIO, unless we miss something, should be reflected in the Gpio Pin Class. So whatever is listening to the GPIOs, whether it's I don't know, any kind of peripheral, interrupts, whatever. And then the other way should also work. So I think we are we did pretty well today. Like, we implemented most of the PIO logic. We are still missing like this clock divider and the exact mechanism for clocking. It's still not perfect. And also this auto push and pull. Let's see what other to-dos we have. So we have output pin wrapping after 31. And what else do we have? Less to-dos than last time. We have this move status. Also move status. We still need to do that. And what else? Set out pins. We know now that it wraps. We have seen this in the datasheet, so we don't need to do. And that's automatic push. I think we have like this. And automatic pull and automatic pull, and there is like this flag to set, and then there is this, yes, there is like something similar with the auto push that we'll check. Yeah, pretty much. Oh, and out sticky, we should also take care of that. Yeah, there is like this debug register. I think we still don't implement it, but yeah, just for the sake of completeness, we will implement those debug bits. So yeah, so I think we are pretty good in terms of how much we have achieved today. Let's just see why it's unhappy. Yeah, there is this unused variables. We don't need it. Then here there are probably a few unused variables as well. Input sync bypass. What's that? I think it's like something that we shouldn't really worry about for the simulation. Yeah, it just yeah, just the like read write register. We should probably do it next week. Just, you know what, let's do it real quick. Just reading and writing from it shouldn't take too long. So radio 32. Yeah, comes right before pad out. Where is pad out? Case return this.input sync bypass, and let's also do the write. So What comes after those IRQ flags? I think so, yeah. Case input sync bypass this dot input sync bypass equals value break, and let's define this variable. Just 0, right? I think it's sync bypass, yeah, it's 0, so one less thing to worry about. And we have those fdebug bits, and that's in to do, so we can keep them as warning for now because we still need to implement those. I think it's nice to see that we already implemented some of them. Yeah, something small for next time, or if any of you want to send any pull request for those missing features, or more importantly, if any of you feels like sending more tests, that would be great. Yeah. What did we change in the test file? Oh, just remove this and just fix this comment here. Yeah, just fixed. So we haven't changed the test logic, just like comments and stuff. And yeah, I think it's a good time to commit. So what was the issue number? PIO mostly done with. That's 61. Still missing, and maybe we are missing a few more things, but at least for the most part this implementation should be good. Yeah, we have like more than 1000 lines of code as guessed, and it will probably get a bit thicker on the next time. Yeah, missing clock divider basically, and clocking in general, auto push pull, out pin, move status, out sticky, fdebug, and there's still probably there are some other features controlled by this Gpio, PIO registers, yeah, by this exec control that we haven't talked about. Like, yeah, we have this exec stalled that I don't think we have done, and the inline out, I don't even know what's that, but I don't think we have this in our code. I don't remember. I've seen this, so, and I guess, yeah, these are like related for sticky probably. Wrapping, yeah, we need to implement wrapping. That's important. And yeah, this is like the status we already have. I think wrapping is like the most important one. Wrapping of PC. Okay, out sticky, fdebug, exec stalled. Yeah, I don't have any idea what is this, but we'll figure it out next time. All right, so I think with that we can cheerfully commit this and push it, and I will make a release. Probably it will be a major release because there is like this new feature. So I mean minor 070, I think. Yeah, 070. I'll make it right after the stream. And before I say goodbye, just one more thing, one more update. Next week we are not going to have a live stream. Sorry, Mark, until you managed to secure this slot in your calendar. So next week I'm in a conference. I'm actually setting up for a conference. I've been working on this name badges for the conference. So we'll have the conference next week. So I will be busy setting up those those badges, those smart name badges for the conference, but that's a story for another time. So next week we are not going to have the live stream in the usual Tuesday slot. Maybe we'll have a spontaneous live stream. I still don't know. The course will be done by then, so there will be no real urgency. But if any of you do want me to have a live stream, maybe on Friday or some other day, just let me know on the Discord and we can probably arrange that if you miss me. And other than that, I wish you a great rest of the week. And thanks for all the comments in the chat. And if you feel like sending any pull requests for the missing features, then please go for it. I will be reading your code and giving feedback on GitHub until we hopefully get to merge it. And thank you for joining. So see you next time. And until then, bye-bye. Bye-bye. Bye-bye.